This 3D landscape represents the baseline assumption of standard thermodynamic models. Systems inevitably move downward to a single point of equilibrium. When a disruption strikes, models classify it as a temporary perturbation. The deviation is absorbed and the system returns to baseline. But philosopher Gilbert Simondon and historian Thomas Kuhn independently concluded that complex formations actually require unresolved tension to survive. In this active metastable network, nodes form multiple clusters that continuously shift and push against each other. Here, structural tension is the engine of persistence. Both thinkers identified this structural necessity through historical observation, though neither possessed the mathematical architecture to formally prove it. If tension is a requirement for persistence, standard models are blind to how biological, social, and epistemic formations actually endure. The Recursion-Collapse-Recombination mathematical framework, RCR version 32, provides the formal specification that Simondon and Kuhn lacked. The RCR equations mathematically prove that under specific axiomatic conditions, systems are structurally forbidden from reaching a state of equilibrium. This ledger demonstrates structural equivalence, the condition-by-condition translation of philosophical theories into mathematical axioms. This establishes a formal test of the conditions under which internal tension becomes mathematically irreducible. Mapping these domains together elevates historical philosophy into testable mathematical theorems. Simondon argued that individuation happens within a state of tension, and that a system never fully exhausts its original pre-individual charge. Simondon's pre-individual field maps to the first three RCR axioms, which establish bounded energy, a pull toward consensus, and continuous stochastic activity. Simondon's central mechanism is transduction, a process where structuration propagates through a field by responding to the field's current state, rather than following an external template. Transduction maps exclusively to axiom A4, the rule for endogenous attractors. In this network, you see axiom A4 in operation. The attractor responds to the data field, and the field simultaneously reorganizes around the attractor. Axiom A4 provides the exact minimal mathematical architecture required for transduction to function. This line graph tracking mean absolute deviation illustrates Theorem 3. The disparity fluctuates, but it hits a hard mathematical floor strictly above zero. Because this deviation cannot reach zero, complete consensus becomes a strict repeller. The system is forced to remain active. We can test if this tension is genuinely necessary for survival through a knockout analysis, systematically removing axioms to observe the result. If we cross out axiom A4, removing the individualizing constraint, the complex network flatlines, collapsing into a single static node. This causes the system's activity score to drop from 2.039 to exactly 1.000, the mathematical floor for a dead single-point equilibrium. Removing both the structural attractors and the recombination force results in complete system divergence or pure consensus. This knockout process proves that removing structural tension causes immediate equilibrium death. This map of Ptolemaic orbits illustrates Thomas Kuhn's assertion that the routine operations of a scientific paradigm inevitably generate the anomalies that disrupt it. Kuhn observed that right before a paradigm breaks, the field becomes increasingly noisy and uncertain, a state he called pre-crisis volatility clustering. Kuhn lacked a mechanical account of the conditions that force a system to generate this crisis internally. The Model 5 equation provides that account, shifting noise amplitude from an external parameter to an internally generated function. The T variable represents the active tension between the system's differentiating pressure and its consensus-maintaining pressure. Theorem 5 defines the amplitude of noise in the system as a bounded mathematical function of that internal conflict. This means mathematical uncertainty peaks precisely when a community works hardest to maintain its consensus. Model 5 provides the strict formal derivation for the mechanics behind this Kuhnian volatility. This Venn diagram visualizes corollary 1, the point where the theories of Kuhn and Simondon converge. The math establishes a nesting logic. Any system producing a Kuhnian endogenous crisis automatically satisfies the conditions for Simondonian metastability. Ludwig Boltzmann's thermodynamic H-theorem provides the historical precedent for this type of proof. Boltzmann derived a macroscopic necessity, that entropy cannot decrease, strictly from the microscopic axioms of colliding particles. RCR theorem 2 follows the same logical program, but in the opposite direction. It derives from axioms the proof that disparity cannot reach zero. By establishing this permanent lower bound, RCR identifies structural resistance to equilibrium as a macroscopic necessity that holds for all time. Mathematics operates strictly on a structural state space, which imposes permanent limits on what formalization can reach. As we see in the work of Lavoisier, RCR maps the boundaries of a scientific revolution, but cannot recover the historical particularity of the events themselves. Equations cannot explain why a specific catalyst emerged when it did, nor can they account for the specific duration of a historical paradigm. This structure also fails to capture the phenomenological human experience, the disorientation of living through a shift in the world itself. The RCR framework acts as a permanent boundary, marking the point where philosophical intuitions translate into structural law.